My talk today is called Swimming in the Data River, or When Streaming Analytics Isn't. So what I'm going to be talking about in this talk is sort of a whirlwind tour of what's going on in the streaming analytics space, and a little pet peeve of mine that we'll get into in a bit. But first, who am I? I'm Gian Merlino. I'm a committer and PMC member on Apache Druid, which is a project incubating at Apache right now, a real-time analytical database. I'm a co-founder at Imply, which is a company built around Druid, and I spent the last 10 years or so working on scalable systems, a lot of them open source. We want to talk about today. So first I want to talk about what I mean by swimming in the data river. So it's this sort of evolution from the old school of data warehouses to the new world of streaming and how we got here, and also where we're going. Talk a little bit about streaming analytics. Talk about Druid, of course, because that's what I work on and I'm very excited about it, and how that fits into the whole world. And then also Druid is open source. You can probably tell from the fact that it's got Apache in front of the name. So do try this at home, how you can join the Apache Druid community. First off, rolling down the river. Let's talk about warehouses, rivers, all that good stuff. So this is a good slide. This is a slide everybody puts up and then says, let's talk about how we're better than this. So it's everyone likes to dump on data warehouses. I'm not super creative, so I'm going to do the same thing. Data warehouses, they're a thing. They were really the first way that people did meaningful business analytics on data. Super popular starting from the beginning of the database world in the 70s, and really the unquestioned kings of analytics until the dawn of the big data era in the early 2000s. They've got a few well-known issues. One issue is you have to do an ETL process before you get data into the warehouse. Near the end of the data warehouse era, a lot of the data warehouse vendors were talking about doing ELT instead of ETL, so loading first and then transforming rather than transforming and then load. ETL, of course, stands for extract data from where it is, transform it into a useful form, and load it into a database. But even with ELT, you still have to get it into this relational format before it can be loaded into a data warehouse. So there's still work to do, even to do a pure load and then transform later. So that's a downside. It means that a lot of people were just not able to get data into these things at all and were just dropping it on the ground. Another one of the well-known issues is that all these apps on the side, does this work? Yeah. All these apps on the side are very thin querying apps that do all their computation inside the data warehouse. So they can only do what the warehouse lets them do. They can run SQL, they can, some of them let you run stored procedures, but they are fundamentally sort of these platforms that embed both storing and computing in the same system, and so they're a bit rigid. So where did that go? That famously is starting to get replaced by data lakes about maybe 10, 15 years ago. Data lakes are interesting. So these are what really came about in the dawn of the big data era, and they're interesting because if you think about it, one of the cool things that they do is they push ETL later. You can put raw data into a data lake. You can transform it later. There's no real reason this had to be concurrent with the dawn of the big data era. Nothing about this is a big data thing. It's sort of just for, I guess, as an accident of history. We got introduced to big data and got introduced to this concept of just loading raw data, unstructured data, semi-structured data, and transforming it later around the same time. The same set of tools empowered both. But I think of them as sort of separate things. And then the apps that go on top of this are much bigger apps. So you have, the modern data warehouse is actually, you can think of it as a SQL app for a data lake. That's something like Hive or Presto, I would think of it as more of an application than a traditional data warehouse. Although you can do a lot of the same use cases, it's an app for a data lake rather than a data warehouse. You can do machine learning and AI on top of these things. You can load data in other kinds of apps, time series databases. So having this explosion of possibility out of apps is one nice thing we got in the big data world. Not just the ability to scale, but also the ability to be much more creative with the kinds of applications that we use to operate on our data. One of the things that I believe, and one of the things we believe in the Apache Druid world, is that this architecture, while it's really exploded in popularity over the last 10, 15 years, is not going to last as long as data warehouses did. Data warehouses reigned for 40 years. I think they'll be replaced by data rivers, so streaming architectures. Streaming architectures are, you get all the same benefits as these sort of data lake, big data architectures. You get to have really big creative apps. You get to load unstructured, semi-structured data, and then figure out what to do with it later. You get all the same benefits, but everything's happening in streams in real time instead of batch delivery. So that fact means you get all the benefits plus this one additional huge benefit of everything happening in real time and being able to react to data as it happens. To me means that this architecture is the one that's going to last the next 40, 50 years. You can even see that one of the things the architecture does, the data lake's not going to go away forever. There's still reasons you might want to do the sort of have this big area of storage to do batch computation in a generic way, but it becomes sort of subservient. You sort of have a tributary from your data river into a data lake. That's that bottom right application. It's still going into S3 or HDFS or whatever, but that's not the primary way you think about interacting with data. So with that being said, let's say we want to go to a streaming architecture. How do we do it? It's a really crazy, brave new world. All the applications have changed. We just went through a world where all the applications changed when we moved to big data. We threw away all of our data warehouses. We threw away our Postgres, and now we have Hive and Presto. And now we're talking about going to streaming architectures, and we have to throw it all out and start over again. It gets confusing and weird. Confluent, a company based around Kafka, they're sort of like Kafka, sort of like for Kafka what Imply is for Druid. Has this cool picture they put on a lot of their talks and blog posts that is a really neat looking streaming architecture that goes around a streaming platform. Very kind of them to write the word streaming platform there and not Kafka. They're being very generous. But it still doesn't tell you what you want to do. It's a cool picture. It's a cool picture that looks really neat and tidy, but there's a lot of questions. Questions like, how does data move between these systems? What are these little gray lines are everywhere? What are those gray lines? You have a little box that says monitoring. What does that mean? Is that alerting? Is it charting? Is it observability? Is it APM? You have a box called security. That seems weird. Is that an application? Is that a set of requirements? Is it just there because we want to have the word security in here somewhere? What does that mean? You have search and NoSQL on the side. But what are you doing with them? You have apps on the top. Are search and NoSQL apps? Do they need apps? Like, I don't know. What's going on here? So there's a lot of questions. And what I'm thinking is let's start simple and let's talk about just some basic things we can do with streaming data. So here's a much simpler picture. There's two boxes and there's one arrow. I have an app and I have a stream hub. And the stream hub is like Kafka, Kinesis, Google PubSub, whatever. I have an app using the library for that stream hub. They all have their own libraries. I'm pushing data into it. Okay, that's cool. Now I have data in there. Maybe I'm pushing data about what people are clicking on my site, whatever. It doesn't matter. I have some data in my stream hub now. There's other ways I can get data in there. I can do what's called change data capture, where the app uses a transactional database to do its thing. So I have a shopping cart, and when I put something in my shopping cart, updates a record in MySQL, and then I have some change data capture running from MySQL into my stream hub. So every insert and update and delete in MySQL triggers a message appearing in my stream hub. So I can do this. That's another way of getting data in. I can also get data out. So what do I do once I have data in my stream hub? I can get it out. I can put it back into a data lake. So I can use my stream hub as a way to get data into a data lake. That's a very basic use of a stream hub, but for a lot of people, it's actually the first thing they do with it. I can put it into a database, so I can change data capture out of a database and then put it back into a database. Nothing wrong with that. And I'm using something like Kafka Connect or Kinesis Firehose for this. Those are data movement tools, data pipeline tools. I can use it for microservices to talk to each other. So I can have service number one, service number two. Service number one can call service number two directly, or it can write a message to my stream hub, and service number two can read it. This is sort of like a message passing type of use case. It's useful. It's a little bit overcomplicated in this diagram. You're thinking, why is it here? But there's some reasons. It decouples service one and two. It means that if service two goes down, service one does not need to be blocking forever writing to it. It also means that if instead of service number two, there's service number 2, 3, 4, 5, 6 that all need that same output from service one, rather than service one having to write to 6 different services every time something happens, it can write to the stream hub and that can get broadcast out. So there's usefulness in this. Another basic thing you can do. But what I'm here to talk about is analytics. So let's say I want to do analytics on these streams. I don't want to just move data around. I don't want to just load data in. I don't want to just communicate between microservices. I want to do some analytics on this streaming data. So I go to the internet. I type in top stream analytics products. What do I get? I get Flink, I get Spark Streaming, I get Azure Stream Analytics. These are all stream processors. So what do these things do? There's a lot of them too. There's not just what's on that list. There's also Storm, Samza, Kafka Streams. There's a Kinesis one, an Azure one, a Google one. There's a ton of these things. Well, the most basic thing they can do is you load data, or you have them, they sit on the stream, they read data from the stream. They can do some alerting, they can do some API calls. So they can do stuff, they can call an API, they can send an alert based on seeing that streaming data. In this world, they're sort of acting like that service number 2 in the microservice architecture, but instead of having to build a microservice, you can just write a stream processing job, and stream processing jobs are much easier to build than a microservice. So they can kind of save you some time. You can also use them to move data. So just like we use something like Kafka Connect or Kinesis Firehose to move data somewhere, I can also use a stream processor to move data. They're capable of doing that. So they're kind of general purpose in that sense. They can do this microservice-y thing. They can do this data movement-y thing. So they're kind of general purpose Swiss Army knives of doing stuff with streaming data. I can also do a continuous query, and that's where it gets really interesting. So a continuous query might be a continuous stream join. Let's say I'm doing stuff with online advertising, and I have a stream of impressions and a stream of clicks. I want to compute a click-through rate. I have to merge those. I have to join those two streams together. And so they can do things like that. They can take two streams, join them into one. They can compute aggregates on streams. So they can run a continuous query and write the results of that query back into the Stream Hub, and then we can send that process data to storage or wherever we want to send it to. But what if instead of taking that continuous query result, instead of just dumping it into S3, what if I want to see it in real time? If I want to see it in real time, then I want a real-time dashboard. So I have a key value store. I run this continuous query. Every time I get, let's say I'm doing a 5-minute aggregation. So every 5 minutes, I have some counters that have updated. I take those counters, I write them into HBase, Cassandra, Redis, whatever, and then I have a dashboard that reads out of there, and I can see these things updating in real time. Maybe I do it every minute. So I have, I call it real time. It updates once a minute. Maybe once a minute's not good enough. Maybe I want to update more often than that. I'm only emitting state once a minute, but some of these stream processors, Flink does this, and a few others do as well, they let you query data directly out of the state store of the stream processor. So instead of having a update once a minute on my real-time dashboard, I can get updates continuously, down to every single message even, because I'm getting I'm getting some aggregates from the key value store, but I'm getting the most up-to-date sort of partial state of the most recent minute from the stream processor state directly by directly querying it. So it's a cool real-time dashboard. I have this continuous query running. I can get unemitted aggregation state, and then I can do key lookups, range scans, in general pre-computation in the key value store. So whenever I have some new widgets I want to show on my dashboard, I spin up a new stream processor job, a new continuous query, have those results be computed continuously, write them into that key value store, load, and visualize them in that real-time dashboard. So this is kind of one of the fancier things you can do with these tools that are called streaming analytics tools. But is this analytics? I don't know, maybe. It's keeping your real-time dashboard up to date. That's cool. But what if I want to do more than that? So this comes to the problem that we're trying to solve with Apache Druid. We're trying to make this happen. At Imply, we make a UI called Pivot that works on Druid. It's a slice and dice UI for flying through your data. And we want this UI to work. It sort of looks like a real-time dashboard if you just have a dashboard view up. But we also want to give people the ability to expand things, fly through things. And Pivot's fairly a recent development. We started Imply a few years ago and then built that on top of Druid. Druid's been around a lot longer. Druid's been an open source project since 2012. And since the beginning of the Druid project, people have been using it to power these interactive user experiences, interactive analytics. And the ad hoc nature of them is really important, the ability to not just have a real-time dashboard, but also be able to drill into it. So you want slice and dice for big data streams. You want to be able to do interactive exploration. You want to be able to look under the hoods of reports and dashboards, and you want fresh data as well. There's a lot of challenges here, that stream processors are not really up to the task of, and that you need some sort of database for. So they're good at scale. Speed, they're good at speed too. You want sub-second response time. Complexity is where things start to fall apart. There's too much fine-grained to pre-compute. So there's too much fine-grained and pre-compute, all possible kinds of drill downs you might want to do. You might want to have the same dashboard. You might want to filter it by country, by city, by product line, by browser. You might want to filter by 3 of them at once. After you add enough dimensions that you want to drill into, it starts getting really unwieldy, and you start to realize that this technique of continuously computing a query and writing the result somewhere is not going to be effective. And that complexity is really driven by the next thing, high dimensionality. So having tens or hundreds of dimensions, you might want to slice and dice on. Concurrency is a big thing. So you want to have the ability of many users to use it. And you want freshness as well. So you want to be able to load from streams. You still want to maintain this ability to see what's happening right now. So of course, we made Druid to try to solve these problems. What is Druid? If you look at the tagline on the previous slide, high performance analytics data store for event-driven data, I want to unpack that a little bit. Just like we're not we're a community project on the Druid side, on the Imply side, we're a small startup, but with the best of them, we had days-long sessions where we tried to come up with the perfect tagline. And I'm so proud of it that I just wanted to say what the things mean. High performance means low query latency, high ingest rates, so 2 sides of the same coin. Analytics means counting, ranking, group by, time trend, that kind of thing. Data store means the cluster stores a copy of your data, and this is where it becomes different from something that's really focused on data in motion. We're storing a full copy of the data in Druid and focused on being able to scan through that data rapidly. So as data gets loaded in, we're not continuously computing the result of a query, but we're putting it into a format that can be scanned very rapidly as any query comes in. And then event-driven data. We want to do fact data like clickstream, network flows, user behavior, digital marketing, I mentioned advertising earlier, server metrics, that kind of thing. If I go back to a diagram like the one that we had before, so how this fits into a Stream Hub world, you still have this sort of continuous query happening with stream processors, but what we're using them for is we're using them for enrichment of data. So we might still use them to join streams together. We might still use them to get additional kind of detail on the original streaming data and make that enriched stream. But then we're doing continuous load rather than a continuous query into an analytical database. And an analytical database is, I would say, the category of things that Druid belongs to. Druid's, of course, not the only one, but an analytical database is a database that's designed to be able to scan through your data really quickly and be able to compute sort of these very read-heavy workloads. Speak SQL. So you have an application speaking SQL to the database. In the Druid world, you have Imply Pivot, that app I showed you earlier, Apache Superset, another Apache friend of ours. Looker is a commercial UI that has support for Druid, or your app here. So like I said, since the beginning of the Druid project, people have been using it to power UIs and applications. The key features of Druid are it's column-oriented. So it's an analytical database, column-oriented, meaning it stores your data laid out by columns. All the data for the same column is going to be laid out in basically a giant array on disk and in memory. That's part of what gives it the fast scan speeds I'm talking about. High concurrency due to its efficiency, scalable to hundreds of servers. The biggest cluster I know about is in the mid-thousands of servers. Millions of messages per second ingested. Continuous real-time ingest, so that sort of continuous load of data from a stream. Indexing all dimensions by default, so that's a cool thing. That means that as you're drilling into things, your queries are actually getting faster and faster because we're using indexes to find what you're trying to drill into and identify those rows. But even if you're not doing a drill down, even if you're doing a full scan of the data set, we're still trying to lay things out such that a full scan can be done in a reasonable amount of time. You query through SQL, and we're targeting query latency of sub-second to a few seconds because we are trying to we're trying to target the ability to build these sort of interactive analytical applications. So use cases, I mentioned these earlier, so I'll skip this. A lot of people are using Druid. So this is a selection of people from the Druid Powered By page. A lot of the original folks that started using Druid from the beginning, so one of the very first users of Druid was Netflix. They're still a user of Druid today. Yahoo's a big user. So it really, like a lot of open source, it starts in the internet world and then kind of meanders out from there to other places. A lot of people using it for a lot of things. One thing that one of the big Druid users, Yahoo, said, they're very nice. They said some nice things about us. They famously invented Hadoop. And they did a piece in InfoWorld a couple years back about how they used to do everything on Hadoop, but now they're starting to migrate some things off of Hadoop as part of that sort of explosion of creativity and applications I was talking about. And Druid's one of the things they're moving things off onto. So the performance is great. Some of the tables they have internally of Druid have billions and billions of events in them, and they're being scanned in under a second. So that's what we're trying to do, and what's actually being achieved at large sites like Yahoo. I wanted to talk a little bit about the architecture. One thing that's interesting is that, let's see, if we go all the way back to, let's see, this slide, and sort of the end state of how you build a real-time dashboard with a stream processor, you see a few things here. You see that you have this key value store that we're using for aggregates that have been finalized. We have this state in the stream processor we're using to read current aggregates. We have this real-time dashboard that's going to be hitting both of them, so that's going to be something generally that's being mediated at the application level. You have this continuous query that's pulling things into really both of those stores. And this architecture is a lot simpler. This architecture is, I just have a load into a database, and the database is doing all that stuff. But internally, it looks like this. So internally, this diagram is actually showing something that's kind of similar to what you would have set up with a stream processor to build a real-time dashboard. You have files and streams coming in on the left-hand side to what we call indexers in Druid. And these indexers are responsible for reading the incoming stream of data. They're responsible for computing partial aggregates on them if you're doing aggregation at ingest time. So there's a mode in Druid where you aggregate ingest time and a mode where you don't aggregate ingest time and just have the raw data. So if you have the raw data, they're indexing the raw data. They're building indexes on top of that. And if you are doing aggregation at ingest time, then they're doing that. So in general, they're going to be dealing with maybe the most recent hour of data. And then we have these things called historical servers. And historicals are dealing with anything older than that, anything older than roughly about an hour. And this is kind of, it kind of feels equivalent to the two ways of querying data in what we had in the real-time dashboard example. And in fact, you actually do query both. So there's a Druid query broker that when a query comes in, it goes to the query broker. The broker just routes it to the appropriate data servers. And it's going to route it to both indexers and historicals. So it'll get the most currently being indexed data from the indexers. It'll get historical data from the historicals. It'll merge it together, and it'll return it to you. And this all happens in about a second or less. So it's under the hood doing a lot of the same techniques, but it's all packaged up into a single database. And of course, one thing that's different about it, one thing that's special about it, is that the data format on disk on the historicals. So the indexers have like a relatively inefficient data format, but they're only dealing with the most recent hour of data. The historicals are dealing with data going back years potentially. So all the data on the historicals is stored in this optimized, indexed, columnar form that can be scanned quickly. And then why this works is computers are fast these days. So indexes are good. They help save work and they help save cost. So the indexes are really there. So if you do have a filter on a query, you're able to resolve that query quicker than you could otherwise and more cheaply in terms of processor power. Like any other horizontally scalable system, you can keep scaling out as long as you want. Druid has the ability to do sub-second queries on almost as much data as you can think of by scaling out, but scaling out's expensive. So we also try to get really good single machine performance. So indexes help save work and cost. But also don't be afraid to scan tables. It can be done efficiently, and in particular, you can get sub-second scans of even very big tables. I want to talk a little bit about integration patterns, so how Druid integrates with other things. This is similar to the diagrams we had earlier. So if you have a stream hub and an event stream coming in, millions of events per second, enrichment happening on the stream hub, so that might be happening with a stream processor, data being continuously loaded into Druid. I would call this a modern data architecture. So it's a stream-oriented architecture where you have the stream hub in the middle, you have enrichment happening on it, you have things going elsewhere outside of that, centered around a stream hub. You actually can do the same thing with a data lake. So I talked about streaming this whole time, about how streaming is the future and blah, 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 and I hope I've convinced you. But at the same time, data lakes are a thing, they're around, and it's, at least for our community, important to support them. So Druid also works with data lakes. And in that world, you're going to have file dumps coming in, hourly or daily or what have you. The data lake is going to be HDFS or S3. You're still going to be doing enrichment, but rather than doing enrichment with a stream processor, you do enrichment with Spark or Hive. So same kind of concept, but different tools. This really kind of, I think to me, is an illustration of the fact that the stream architectures and the lake architectures are actually conceptually very, very similar and organized very similarly. Just streaming versus batch is the main difference. So a slightly less modern data architecture, about 10 years less modern, centered around a data lake instead of a stream hub. And then finally, I want to talk about the community. So like I mentioned, Apache Druid is a community project. I am Druid, and so can you. Everybody's welcome. We have a community site, druid.apache.org. Our old community site is on druid.io. We still have a lot of content there. We're working on moving that content to the Apache site as part of our journey through the Apache incubator on the way to becoming a top-level project. And then I work at Imply. The Imply distribution of Druid, which includes Pivot, is available at imply.io/getstarted. You can contribute on GitHub. All Druid development happens on GitHub, github.com/apache/druid. And follow us on Twitter. And you can also join the community. The mailing list, the dev mailing list, is where a lot of dev discussions happened. User mailing list for user questions. And GitHub for issues, pull requests. All comers welcome. And thank you. Any questions?
I'm sorry, I came in a little late and not super familiar with Druid, but can you talk a little bit about, you mentioned horizontal scalability. Do you guys have any plans to decouple storage from compute, or is it already decoupled? I guess in that direction or in that vein?
Yeah, that's an interesting question. I appreciate you calling that out. I kind of slid over that part in the talk. But in my mind, compute and storage in the way that Druid does things and the way Druid integrates the big data world is both coupled and decoupled. And what I mean by coupled is that the Druid data servers do have the data that they're going to process locally. In a lot of situations, it's already pre-cached in memory. And when it's not pre-cached in memory, it's kept on local disk. One of the reasons we do that is to be as fast as we can be. I mean, people, a pretty typical performance envelope for a well-tuned Druid cluster is that even on huge data sets, queries are happening in 40 milliseconds to a few hundred milliseconds. And that kind of perf, coupling is helpful for that. But decoupling is also useful for data management. I would say one thing that defines big data architectures is you don't have one copy of your data. You don't have your data living in just one system. You sort of have a lot of systems used for different purposes. And to that end, Druid's ingest model is a pull-based model. And it's designed to be able to pull from S3, pull from HDFS, pull from Kafka. So the idea is that it is aware of systems like that and can stay in sync with them, but it doesn't query directly out of them. So what it does is you tell Druid, I want you to make a Druid table based on this Kafka topic. It's not going to query from Kafka, so it's not going to be a decoupled in that sense, but it will stay in sync with Kafka. It'll do a continuous load from Kafka. And as you add stuff to Kafka, it'll also be added to the Druid table automatically. So that's kind of the idea, and what I mean by we try to do both.
I have one. So you mentioned you support a high ingestion rate, and you don't want us to be afraid of table scans, and those both sound great. But disks are shared resources in this scenario, and there are only so many IOs that you can do per second. Is there a tension between those two? For example, at runtime, heavy-duty queries, and then maybe your ingestion rate has to slow down. Is there anything like that?
Yeah, that's a really good question. So if I go back, well, I don't need to go back, but there's sort of people that are running at super high ingest rates. So I had those boxes up there for indexers and for historicals. You actually, for a small or mid-sized cluster, we suggest, for simplicity's sake, running them on the same machines. But for big clusters or clusters that have heavy write loads, we suggest splitting them up for that reason. So you actually have machines, in a 100-node cluster, you might have 15 machines dedicated to ingestion and then 85 dedicated to historical query.